So we're heading into Vesper theories, what's coming next, predicting the shapes. What we're going to talk about today is hybridization, which is sort of the why to the shapes that we get in Chem 20 bonding. The shapes come from mixing atomic orbitals will predict the shape of molecules or molecular orbitals. So we're going to start by looking at Lewis symbols and then fully getting into hybridization. So we're going to look at period 2. So lithium would be the first atom. Beryllium is the second with 2 valence. Boron is the third. Okay. We've got those last two tend to have incomplete octets. Carbon is the fourth. We typically see 4 bonds in carbon. Then we get to nitrogen, and finally we start getting some lone pairs. Okay. Oxygen 6. Fluorine has 7, 3 pairs in a single. Where you put the single doesn't matter. And then finally we get to neon, our noble gas that has full sp orbitals. Then I have this question. Sometimes students ask me before I get to this point. I taught about sp orbitals and the filling up from lowest energy, and this doesn't match that. Lewis theory is doing hybridization. So which of these don't match what we learned in terms of filling 1s, 2s, 2p, 3s, 3p? If you think of lithium, there's nothing wrong there. That'd be 1 electron in a 2s orbital. Okay. What about beryllium? Is that what we would expect quantum to tell us? No. You know, I spread out those 2 dots in 2 different orbitals, but we would have expected it to be a pair. Okay. We would expect to have 2s filled with 2 electrons. But that's not what we do with Lewis symbols, and there's a reason for that. Okay, boron would expect 2s to be filled, to be a pair, and you'd expect just a single electron in p, and that's not what we see in Lewis symbols. It's not what we see in real life. We're really going to focus on carbon. We expect, quantum theory would tell us, would have a pair of electrons, the 2s orbital would be filled, and then we should have just 2 singles. You'd think carbon would have a bonding capacity of 2 because of a pair and a couple singles, but it's not what we see with carbon. It is possible for carbon to bond like that, but not typically. No, carbon is so important for the study of carbon is so important to understand organic life. We've got a whole Chem 30 unit on carbon, and we're going to look at the hybridization of carbon, the mixing of orbitals. Those s and p orbitals mix because they're so close in energy, and we get mixed orbitals that predict our shapes. So we're going to look at mixing all the s's and p's, the s and a couple p's, and the s with 1 of the p's. And we'll predict 3 of the 5 shapes that all Chem 20s need to know about. Okay, and we'll go through all the shapes in the next lesson. So our first shape. So our theme is SPX hybridization, where I'll do P3, P2, P1, and our first of the 3 topics that X is going to be 3. We're going to mix 4 orbitals in total. So I'm going to start with what we learned already. we would expect 2s in carbon to have a spin up and spin down. Okay. I'm not going to draw any of the core electrons. I'm just going to do the valence throughout this hybridization lesson. And then above that in energy would be our 2 p's. Okay. But that's not what we see. We know there's something else going on. Okay. So remember, an S is a spherical orbital. P's have 2 lobes. But what we see is the mixing of those 4 orbitals to make 4 equal energy orbitals. So we're taking all of the S's, or the only S, and all of the P's. That's 4 boxes in total. We're going to mix them all up, and the naming comes from the orbitals we've mixed. So we've mixed them all. We've hybridized them all. When you hybridize them all and get 4 orbitals and start filling them with 4 electrons, there's 1, there's 2, there's 3, there's 4. So I have the same 4 electrons, but now none of them are paired. We get 4 spin-ups. We get 4 bonding electrons. And this matches what we see. Now we're going to get different shapes. Okay, you don't necessarily have to add this to your notes, but you have a spherical orbital and an S. And P's are these double lobes that could be up and down, right and left, or out of the board into the board. The PX, the PY, the PZ. Okay. When you mix them, we get a combination of a sphere and double lobes. We kind of get a big lobe and a little lobe. Okay. And we get 4 of them. So I'm going to do my best to draw these 4 sp3 hybrid orbitals. So I'm going to do 1, sort of up and down. We get a little lobe and a big lobe. That's one of our orbitals. And remember, this is where we can find the electron. We don't know exactly where it is, but that orbital that can hold 2 electrons somewhere within that shape. There's the second. I made that one a little bigger than I wanted. There's the third. And there's the fourth. So we end up with 4 orbitals, big lobe, little lobe. They're all the same, but they're in different, they're not perpendicular to each other, but they're spread out as far as they can in 3-dimensional space. Now, one problem with this is that's a flat projection of 4 lobes spread out. Okay. So that's a flat projection. Okay. So it's not really flat like that. The difference, the bond angle between any of the lobes is 109.5 degrees. If you take 4 lobes or 4 of anything and you spread them out in 3-dimensional space, okay, they end up 109.5 degrees from each other. If it was flat, you'd have 90, 90, 90. So if our world was 2-dimensional, not 3-dimensional, you'd have 90, 90, 90. But our world is 3-dimensional. Okay. So in 3 dimensions, the bond angle is 109.5 in all orientations. Okay. So this is one of the bond angles that all Chem 20s are going to have to know. When you have 4 bonds, 4 separate groupings of electrons, you get this angle. We'll talk about the shape tomorrow. So this is caused by sp3 hybridization. Okay. So we took one S and 3 P's. We're going to leave one of those P's alone. sp2 hybridization. So I'll quickly recap the old. An S, 2S with 2 electrons. We've got our 2P with our 3rd and 4th valence electron. Okay. Then I'm going to do the sp2 hybridization. So sp2 is how many orbitals? 1s and 2p's. So there's only 3 orbitals being mixed now. Okay. And then there's a leftover p orbital. This is how we get a double bond. That leftover p makes the double. Our 4 electrons, 3 of them go in the sp2, which forms the first bond, and the leftover electron goes into the p orbital that's left over, and we get a double. Okay. Now it's going to get a little bit easier to draw. The sp2 orbitals, there's 3 of them, and they're going to come out flat now. Now, because they're flat, what bond angle would we get if we have 3 things spread out in a circle? What's a circle divided into 3 pieces? See, 100, 100, 100, that doesn't work. That's not 360. 120, 120, 120. So that's what I've got to draw off my 3 orbitals. So I'll start going up. Okay. Now I've got to go 120 and do the second one. Then I got to go another 120 and do the last one. So we have a 120-degree bond angle. And it comes out flat. When you spread 3 things out in 3-dimensional space, you don't have something up or down. You get a flat projection. Okay. And then you've got a leftover p orbital. Okay. So we end up with 3 bonds here, and then we get 1 leftover bond, so we can get a double. Okay. So we get a 120 bond angle, and then the double overlaps on top of one of those 3. It's in the same space. That's why we write the doubles right next to each other when we write a double bond, because it overlaps with an existing sp2 hybridized orbital. Okay. I want to take this one step forward. So we had 4 bonds, 3 bonds and a double, and then we'll have 2 bonds and a triple. The least we can do is only mix 2 things. sp2 hybridization. So quickly get out for the 3rd time the old that we don't see, showing just the valence electrons. So there's our 4 valence electrons. We don't see this. I'm going to mix 1s with 1p. That's only going to give me 2 orbitals. The other remaining 2 p orbitals don't mix. They just stay double lobes. So we're going to get 2 bonds now, and then we're going to get some overlap. We can get a p orbital can overlap and make a double, and then the second remaining p orbital can make a triple bond. You know, they're going to be on top of the sps. Okay. Now we only have two orbitals to spread out in three-dimensional space. So what bond angle? We now have three-dimensional space. We're going to put two things in three-dimensional space as far apart from each other. So it's going to be 180. We've got two things in three-dimensional space. We're going to have a 180 bond angle. So I'm going to draw my orbitals first. There's my big lobe to the left. Big lobe to the right. And we've got a 180-degree angle between the red to the left and the red to the right. And then on top of that, you would have some overlap. Okay? This is what we're going to see in a molecule if you have carbon with a triple bond. The first bond from the carbon to each of the atom is an sp. So that is one of our sp hybridized orbitals, carbon to hydrogen. This first bond is another sp. Then the double is from one of our p's, and the triple is from one of our p's. Okay? The double and the triple are a fundamentally very different type of bond. Those p's are fairly easy to break, and in Chem 30 we study reactions where they break. But that first bond, that sp in this case, the hybrid orbital, is really hard to break. We can't go in the lab and easily break it unless we like burn it and do a combustion reaction. Okay. The hydrogen to carbon would be a nice straight line, would be a 180-degree bond angle. The more bonds carbon has, the more that bond angle will get smaller. Okay. 2 bonds, 180. 3 bonds, it'll drop to 120. 4 bonds, it'll drop to 109.5 and form a different shape. Okay. So that is hybridization, okay, in carbon. Now I'm just going to flip back and maybe put some molecular examples. This is more of a lead into tomorrow for the different hybridization. So we started with sp3, carbon forming 4 bonds. S and 3 p's makes 4 bonds. So hopefully you have a little room in your notes. So when does carbon form 4 bonds? In something like methane, we get sp3 hybridization. Carbon. Now, I have to flatten this out. I can't do a 3-dimensional drawing, so that's up, and then we've got 3 sort of coming down, but none of those are in the plane of the board. Think of those as think of that as a 3-legged stool on the bottom with one thing sticking up. They're not flat. So methane. So ultimately, you're not going to be asked a lot about the hybridization. You see 4 bonds, it's sp3, but 4 bonds is 109.5. Okay? Or 4 groupings, lone pairs would also count. Okay? So you get the same hybridization here if you have a lone pair and 4 bonds. That's also sp3, 109.5. Okay? So 4 distinctive groupings of electrons, sp3. 3 grouping of electrons and a leftover p, which means you have a double, you're going to get sp2. So we're going to see this with a carbon-carbon double bond. Okay. Now we've got 2 carbons. I'm going to put an arrow in to focus in on 1. Okay. That carbon is sp2 hybridized. Okay. I'm actually going to point my arrow to all those hybridized bonds. Okay. So that one is sp2, that one is sp2, there's the third sp2, and that extra one is a p, leftover p. Okay. There are 3 groupings of electrons. Okay. 3 sp2 hybridized electrons, we get that 120-degree bond angle, which is kind of the way I drew it. Okay, so it's flat, sp2 is flat, and we get 120, 120, and then 120. Okay, so different bond angle. And then last, we get to where we finished off. sp hybridization with 2 p's left over, and we get that 180. We get a straight molecule. So that's hybridization in carbon or hybridization in any molecules. I did that ammonia, NH3 with the lone pair. It applies there. It allows us to predict any bond angle.